So in this lecture, we will be discussing water hammer. So what is a water hammer? Water hammer is a pressure surge or wave resulting when a fluid in motion is forced to stop or change the velocity. A water hammer commonly occurs when a valve closes suddenly at the end of a pipeline system and a pressure wave propagates in the pipe, which is also called as hydraulic shock. So here in this example, water hammer occurs when we close a valve or a gate in a flowing pipeline system, and with that sudden stoppage of that movement of the fluid along the pipe, so it will cause what we call a hydraulic shock along this pipeline. So um, parang sa traffic or anything that flows when it is suddenly stopped. So there is congestion and where the point where a path is closed. So there's that's when water hammer occurs when it comes to sa pipeline system natin. So what are the effects of water hammer? Number one is it damage the pipes, fittings, and valves, or any connected equipment causing leaks and shortening the life of the system. So if it is not properly, or pipeline system is not properly designed that can withstand water hammer, so this would be the after effects or one of the major damages that it can cause on our pipeline system. And number two is bursting of pipes. So our pipelines might burst when there's water hammer. And water hammer can have devastating effects on the pipeline system. So here are some sample pictures of the damage caused by water hammer. So there's bursting of pipes, so there's leakage along the pipeline, and we don't want that to happen on our project or on the structure that we are building where on our pipeline system. So here we will study on how to compute the equivalent pressure caused by water hammer, how the time of closure it really affects on the water hammer itself. So uh, let's start now discussing what are the solutions, equations that we're going to use here in this topic. So let's start first with wave celerity. Wave celerity is just the equivalent velocity of the sudden stoppage of the flow of the liquid. So when initially we have a velocity, okay, we have a velocity of the liquid flowing through the pipeline. When we suddenly close that, so there is stoppage of flow and there is uh, uh, a wave of uh, velocity of stoppage of the wave or what we call the wave celerity, wherein parang backflow effect dun sa pipeline system natin. So when we suddenly stop the gate or the valve, so parang may opposite velocity that that is being caused along the pipeline. So this wave celerity can be used in determining the pressure acting on this gate. So for rigid pipes, here is the equivalent formula for the wave celerity. So celerity is equals to the square root of the EB over rho. EB is the bulk modulus of elasticity of the fluid, and rho is the mass density of the fluid. For non-rigid type of pipes, here's the equivalent solution for the celerity. The square root of the bulk modulus of elasticity of the fluid all over the mass density of the fluid multiplied by 1 plus bulk modulus of elasticity times the diameter of the pipe divided by the bulk modulus of elasticity of the pipe wall and multiplied by the thickness of the pipe. So here it is. So here are the terms for each uh, variable. Okay. So for the pressure change due to the water hammer, the time for the pressure wave to travel and back again along the pipeline is computed using this equation, 2L over the celerity, where L is the length, okay, the length of the pipeline from the upstream going to the gate or valve itself. Then C is your celerity, the computed celerity. For different time of closure that we are going to do on the valve or gate. So there's a different solution for us to compute the pressure change due to the water hammer. The first one is to when we have instantaneous closure, when this is the immediate stoppage or closing of the gate. So we immediately close the gate or the valve. So that's when instantaneous closure takes place. And where we are going to compute the pressure change due to the water hammer, it is computed using this solution, rho CV, where rho is the mass density of the fluid, C is the celerity, and V is the velocity, the initial velocity of the fluid along the pipe. For rapid closure, so uh, when you say we were a little bit slower in closing the gate, so if we have a given time of closure here in closing the gate or the valve, if we have computed that it is less than, okay, if the time of closure in closing the valve or gate is less than the time for the pressure wave to travel and back again, or the 2L over C, uh, we can use also the solution rho CV. That's for rapid closure. So both instantaneous closure and rapid closure is uh, when it comes to time of closing the gate or valve is a bit faster. But unlike the slow closure, when the time of closure is greater than the 2L over C, so here is the equivalent solution for the pressure change due to the water hammer, where 2L V pro over the time of closure. So L is the length of the pipe, V is the velocity, and rho is the mass density of the fluid, and Tc is your time of closure. So let's now start solving some problems here on this topic. So this is past board examination problem, May 2011, CE board. So a valve is suddenly closed in a 200 mm diameter pipe. The increase in pressure is 700 kilopascal. Assuming the pipe is rigid and the bulk modulus of water is 2.07 times 10 raised to 9 Newton per square meter, compute the celerity, compute the velocity, and if the length of the pipe is 650 meter long, compute the water hammer if the valve is closed in 3 seconds. For number 1, let's write down first the given. So the given are, we have a diameter of 200 millimeter pipe. The increase in pressure is 700 kilopascal. So increase in pressure, given na yung ating water hammer pressure, 700 kilopascal. And we have the bulk modulus of water, 2.07 times 10 raised to 9 Newton per square meter, or Pascal. This is also Pascal. Number one, compute the celerity of the pressure pipe in meter per second. So for number one, uh, it is said here that it is a rigid pipe. So the applicable solution for the celerity is the square root of EB over rho. So the square root of EB, or the bulk modulus of elasticity of water, which is given here, is 2.07 times 10 raised to 9 Pascal divided by rho. Rho is for water, if it is not given, our standard is 1000 kilograms per cubic meters. So 1000 kilograms per cubic meter. So just to check if the equivalent unit that we're going to solve here is in meter per second. So given that Pascal is Newton per square meter and is divided by kilogram per cubic meter, so and Newton is kilogram meter per second squared, so cancelled out to, okay, and we bring that up, that will be meter squared, and kilogram is cancelled out, meter squared per second squared, and taking the square root of meter squared per second squared, the unit is meter per second. So let's solve this. Square root of 2.07 times 10 raised to 9 over 1000 kilograms per cubic meters. So the answer is 1438.749 meter per second. That's the answer for the celerity for instantaneous closure. So for number one, C is 1438. The nearest answer is 1439. Letter B. For number two, okay, compute the velocity of flow in meter per second. So what will be the velocity? So for instantaneous closure, we have, okay, we are not yet in number 3, where we are not yet considering this time of closure in number 3. We're still in number 2, that if we don't have a given time of closure, we can assume first that it is an instantaneous closure in solving this kind of problem. So for an instantaneous closure where TC is 0, we can solve the increase in pressure as rho CV. So since V is required, it means that V is pH over rho C, rho times C. So substituting all the given here, we have 700 kilopascal. We convert that into Pascal, we just multiply 1000. Then rho, 1000 kilograms per cubic meters. And C is 1438.749 meter per second. So just to be consistent in unit, okay, we have Pascal here because Pascal is Newton per square meter, and kilograms per cubic meters, meter per second. Okay, so when we convert all that, the unit for Newton is kilogram meter per second squared per meter squared over kilogram per meter squared meter per second. Okay, so when we cancel all of the units, okay, what will remain here is the unit meter per second for the velocity. Okay, so the velocity is equals to 700 times 1000 over 1000 times 1438.749 749. Okay. So the velocity is 0.4865 meter per second. Okay. So the velocity number 2, it's letter P. Or number 3, if the length of the pipe, if L is 650 meters and the time of closure is 3 seconds, what will be uh, the water hammer pressure? Okay, so the time of closure is 3 seconds. We have to compute first 2L over C, the time. So 2 times 650 over C, which is 1438.749 meter per second. Okay, the unit that will remain is second. Okay, 2 times 650 over 1438.749. So time is 0.9004. So the time of closure is greater than T. So the solution that we are going to use in determining the pressure due to the water hammer is 2L, okay, rho V over time of closure. So 2 times the length, 650 meters, rho 1000 kilograms per cubic meters. Then we have the velocity, which is equals to velocity given 0.4865 meter per second, and the time of closure is 3 seconds. Okay, so the equivalent unit that we are going to have here is in Pascal. Okay. Cancel, it's meter per second squared. Then kilogram meter per second squared is Newton per meter squared. So this is Newton per meter squared when we compute this. Okay, 2 times 650, 2000 times 0.4865 over 3. 210,816.667 Pascal or Newton per meter squared. We convert this into kilopascal, just divide it by 1000 kilopascal. So in the choices, we have a unit of kilopascal. So the answer here, the nearest answer is 210.83, letter B. That's for number 3 question. So that's for example number 1. Okay, that's how you solve the water hammer pressure and its celerity, wave celerity. Next, number 2 is still May 2011 board examination problem. So we have oil having a density of 870 kilograms per cubic meter. So this is oil. We have given mass density. Then the velocity is 1.2 meter per second in a rigid pipe. 0.5 cubic meter of this oil is known to decrease by 0.001145 cubic meters. So we have a given change in volume, okay? Change in volume of 0.001145, a decrease in volume, cubic meters. And the initial volume is 0.5 cubic meters. Under a pressure increase of delta P of 3000 kilopascal. So the pressure increase that we are referring to here is the pressure that causes the oil to decrease a volume of 0.001145. It is not yet the water pressure due to water hammer. So it's not the pressure caused by the water hammer. It is just the pressure that is applied on the oil for it to cause reduction of volume by 0.001145. So where can we use this? In number one, it is asked here what is the bulk modulus of elasticity of this oil. So as we recall in physics, in computing the bulk modulus of elasticity of any material, okay, it is said there that the bulk modulus of elasticity has a formula which is just the ratio of the change in pressure over the change in volume over the initial volume. So using this equation, we can compute the bulk modulus of elasticity of the oil. We have 3000 kilopascal all over the change in volume, which is 0.001145 cubic meters over 0.5 cubic meters. The bulk modulus of elasticity is equals to 3000 over 0.001145 over 0.5. 131 0043 1668 kilopascal. If we convert this into scientific notation, we have 1.31 times 10 raised to 6 kilopascal. This is your answer for the bulk modulus of elasticity of the oil. In the choices, what we have is letter D. For number 2, what is the celerity of pressure wave? Okay, there's no time of closure here, so we can determine that later. But first, we have to determine the celerity. Celerity, this is a rigid pipe. So the celerity is the square root of EV over rho. So EV over rho, we have 1310043. We convert this into Pascal unit to be consistent with the unit that we use, so that our answer should be in meter per second for the celerity. So we multiply 1000 on this bulk modulus of elasticity to convert it into Pascal. So this is Pascal divided by the given mass density, 870 kilograms per cubic meters. So the celerity is square root of 13100436668 over 870. The answer is 1227.109 meter per second. Letter 1227, letter A. For number 3, what is the water hammer pressure expected for instantaneous closure? So instantaneous closure, TC is 0, so the pressure due to the water hammer is just rho C times V. So substituting all the value that we have identified in the previous problem, we have celerity of 1227.109 and velocity of 1.2 meters per second. So the answer is 128.110.1.796. The equivalent unit that we are going to have here is in Pascal. If this is in kilopascal, just divide it by 1000. 1281.102 kilopascal. That's your answer for number 3. 1281, letter B. Okay? We're done with number 2 situation. So for our last example, this is May 2010 CE Board exam problem. Water from a reservoir flowing through a pipe having a diameter of 600 mm with a velocity of 1.75 meter per second. So I'm going to be given first diameter 600 mm, velocity 1.75 meter per second, and it is completely stopped by a closure of a valve situated 150 meter from the reservoir. That's the length. Assume that the pressure increases at a uniform rate and there is no damping of the pressure wave. The pipe has a thickness of 20 mm. Bulk modulus of water, okay, is 2.2 times 10 raised to 9 Newton per square meter, and the modulus of elasticity of steel is 1.4 times 10 raised to 11 Newton per square meter. Compute the celerity for number 1. Number 2, the bulk modulus of elasticity of the pipe and water, the composite bulk modulus. And then third question is the pressure on the pipe after the closure of the valve in kilopascal. So for number 1, the celerity that we are going to use here is it's either for a rigid pipe solution or a non-rigid pipe. So as we can see here, it is not mentioned in the problem if it is a rigid or non-rigid pipe. But if it is mentioned that it is a rigid pipe, it's clearly that we can use the solution, the square root of EB over rho. But here in this problem, it is indicated here that the thickness, the length, the diameter of the pipe, they are all given. So it is a clue that it is a non-rigid pipe because we are going to use these parameters that are given, such as the thickness and diameter, and as well as this bulk modulus of elasticity of the steel. Okay, since we have a steel pipe. So the solution that we are going to use here is the long one for the non-rigid pipe. We have a formula of EB over rho multiplied by 1 plus EB times the diameter over E times the thickness. Okay. Substituting all the value with a consistent unit that we are going to use, it should be in Pascal for the modulus of elasticity. So the Newton per square meter is in Pascal, substituting the value of bulk modulus of elasticity of water over mass density is 1000 kilograms per cubic meters multiplied by 1 plus 2.2 times 10 raised to 9. How about the diameter? Are we going to use millimeter or in meter? So it doesn't matter because it will be cancelled if we use millimeter for both the diameter and thickness. So I will just use here millimeter. And E is 1.4 times 10 raised to 11 Newton per meter squared multiplied by the thickness, and it should be in millimeter also if we use millimeter on the diameter. Okay, so this is your solution. We cancel the units here and this one. So the remaining unit is Newton per meter square divided by kilogram per cubic meter. The equivalent for that, when we take the square root of those units, is in meter per second. So solving this solution right here directly, calculator, we have 1000 times 1 plus E times 600 over 1.4 times 10 raised to 11 is 20. Okay, the answer for the celerity is 1222.761 meter per second. Or that's 1223. Letter B. Second question, what will be the composite bulk modulus of elasticity of pipe and water? So for the composite bulk modulus of elasticity of pipe and water, in this kind of question, it means that for the equivalent bulk modulus of, of the elasticity of pipe and water, we can compute that by simply considering it as a rigid type of pipe. So using the celerity computed for a non-rigid pipe, the equivalent bulk modulus of elasticity for a rigid pipe is your bulk modulus of elasticity, or the composite bulk modulus of elasticity of pipe and water. So using the solution for the celerity of a rigid pipe, EB over rho, we can compute this bulk modulus of elasticity. So rewriting the solution, we can have c squared times rho. Okay, so c is 122.761 meter per second raised that to 2, and rho is 1000 kilograms per cubic meters. So that's it. And raised to 2 times 1000. Here's your answer, 1495.144463, or we change it to scientific notation, 1.495 times 10 raised to 9. The unit is in Pascal. This is in Pascal. Okay. So the answer is letter D. Okay. That's for number 2. For number 3, compute the pressure of the pipe after the closure of the valve in kilopascal. So there's no given time of closure. This is an instantaneous closure. So the pressure is just rho CV, 1000 kilograms per cubic meters, times the celerity, 761 meter per second, and the velocity is 1.75 meter per second. So the equivalent unit for this is in Pascal. The computed unit, 1000 times 1222.761 times 1.7. Okay, 2139831.75 Pascal, or in kilopascal, 2139.832 kilopascal. 2139 or 2140. So the nearest answer is letter C. Okay, so that's the answer for this situation. Okay, so that ends our lecture, class.